All right. So for this part, I will largely use my handwriting. So we will actually talk about 3 different tests for the last part. So let's go to their definition first. Okay, so let's first talk about Wald test. Versus score test versus LRT, likelihood ratio test. Okay, so I'll try to give you the high level ideas behind each test and argue what is the best use of each case. Okay, for the Wald test, the foundation is asymptotic normality. And the definition is, and for all these, it's about testing a null hypothesis. Let me put it here. Null hypothesis, theta being theta 0, versus alternative hypothesis, theta not equal to theta 0. That's the starting point. The Wald test statistic is using the MLE, theta hat minus the value under the null, theta 0. We square it, and then we divide it by the variance of theta hat. That's the thing. So you would need to obtain theta hat as the MLE under alternative H1. So essentially, when you calculate MLE, it's unconstrained. You're just using your data to find the MLE, not constrained by the null hypothesis. And but the key challenge here is what? The challenge here is how do you obtain variance hat of theta hat? Because the variance itself may rely on some unknown parameters, right? So how do you estimate this well? So this challenge is that this estimation may be inaccurate when n is small. When you have a small sample size, you cannot estimate this variance well. And also, since we said it's relying on asymptotic normality, which will say that theta hat is asymptotically normal with no, we're actually having theta hat is asymptotically normal with mean theta 0 and variance theta hat. So we're relying on this fact to construct this Wald statistic. And it's basically standardized version of this. So essentially, this will follow under the null chi-square 1 because we are standardizing it, and then before we do it square, it's close to standard normal. That's the foundation. But if your sample size is too small and asymptotic normality does not hold well, then this will not hold well. So it's just an asymptotic result. And also, as you can see that we would require to do MLE under the alternative model. And if MLE is difficult to obtain, like numerically, this is another challenge. So one challenge is that you may not have a good estimate of challenge 1. You may not have a good estimator for the variance. Challenge 2, asymptotic normality may not hold well on small sample size. Challenge 3, MLE theta hat may be difficult to compute. So these are the things we must consider for the Wald test.
The challenge is estimate both variance, right?
Yeah, estimate all of the variance. Yeah, because the variance may rely on some other parameters. Like in the linear regression case, the variance will require your estimation of the sigma square, right? But if your sample size is too small, estimating another parameter may be difficult. Yeah. So essentially, Wald test, when to use it? I would say simple, good estimator, and large N. So for linear model, this is okay because you know the asymptotic normality does hold well for the beta, for the coefficient. And if you're interested in estimating one single beta coefficient, and asymptotic normality holds without a problem, MLE, easy to compute by least square. And if you have a large reasonable N to make the asymptotic normality hold and also to make the variance estimation nice, then you can use Wald. So it's just simple. That's it. So that's why, and also it's very intuitive based on asymptotic normality. That's the Wald test we use in linear model. How about the score test? Let's talk about the second thing. The score test, the name depends on the score function. Okay, so essentially the score function is called as theta. It's defined as what? It's defined as the log likelihood of theta's first derivative. So we write partial likelihood, partial derivative, because there may be other parameters involved. But we are just looking at the log likelihood of your parameter of interest, theta. We take the first partial derivative against theta. We call that the score function, okay? And of course, we also have the Fisher information, I theta. We have defined this multiple times. So the score test for the same null hypothesis is defined as theta 0 square of the score at the null value over Fisher information at the null value. This is the score statistic. And the advantage of this is you only need to compute your log likelihood score function Fisher information under the null. So essentially, you only need to fit the null model. And this can be a big computational advantage. The reason is that in the null model, you already set your key parameter theta to the value theta 0. And your only parameters left to estimate are the nuisance parameters. So this can make computation much easier. Yeah, while in the Wald test, you need to fit the full model, right, and do the MLE. You need to get a theta hat. But for the score test, you don't need to do that. Okay, so the score test rationale is if the true value theta is theta 0, so which means if the null hypothesis does hold, then you know what? The score should be close to 0, right? Because the score is the gradient at theta. And if theta happens to be the true value, which means that you expect the log likelihood to be maximized there by theta 0, then the score function value at theta 0 should be close to 0. That's the idea. And we take the square of it because we don't care the sign. It can be positive or negative gradient. That doesn't matter. We just hope it's close to 0. And we normalize this by the Fisher information because Fisher information is the expected value, right? Expected, or is the variance of the score. We have that formulation for Fisher, variance of the score function. So we normalize by the variance, but this overall idea is to make sure the gradient is close to 0. So that's why for both the Wald test and the score test, we reject null hypothesis when the value of the test statistic is too large. and using asymptotics of the score function, which we don't remember. We briefly said something, but not in very detail in this class, but you can easily look it up, asymptotics of score function and the score statistic. We can also show that this also, under the null hypothesis, chi-square 1, if theta is one-dimensional. Depending on the dimension of the theta, if it's k-dimensional, then it's chi-square k. So that's the advantage. Only need to fit the null model once, fast. Okay. Finally, likelihood ratio test. So likelihood ratio test statistic is defined as, it's often called a gamma, big gamma, of 2 times the log likelihood at theta 0 minus the log likelihood at theta hat. Okay, the difference of 2 log likelihoods, one evaluated at the null value, the other evaluated at the MLE. So you see, compared to the previous 2 tests, here the thing is that you need to fit 2 models, the null model and the full model. You need to compute both. So it is computationally most intensive one compared to the other 2. But I can tell you that this one is statistically most efficient. And the intuition here is because likelihood uses full information in your data. You don't lose any information, right? Because the likelihood uses full information of data. Likelihood just captures everything. While the score test doesn't use likelihood, it only uses the score function, the gradient of it, right? And the Wald statistic only use the asymptotic normality, but not the likelihood. So in terms of statistical efficiency, which is what we were just talking about, asymptotic variance and power, likelihood ratio test most powerful. And this is very important when you have small sample size. This is important for small sample size, or small m, because you need it to be efficient. But when your sample size n is very large, like in the asymptotic case, it does not matter. All 3 tests become equivalent. They have the same asymptotic efficiency if you have n goes to infinity. Okay, so this also converge in under the null to chi-square 1. So they have the same asymptotic chi-square distribution, same asymptotic efficiency. The difference is based on sample size. For a small sample size, if you can afford to compute to fit 2 models and compare the likelihood, go with LRT. No question for that. But if fitting this full model on your data is just computationally too challenging or slow, consider score test. Because for score test, you only need to fit null model, which is fast. And it's more efficient, statistically more efficient than the Wald test. The Wald test is actually the least efficient one. It can have many cases that we can break down, especially when the variance is not estimated well or asymptotic normality does not hold well. In particular, if your true value is close to the boundary of your parameter space, then asymptotic normality may have some problem. So that's why Wald test is the least robust, but it's simple. And for the cases where people do use it commonly, like the linear regression, it is the case where people don't worry too much about its risk. And also, yeah, you have package to use, right? So it's easy, intuitive. So that's why every test still has its application domain. But score test is actually a very interesting middle ground because it's faster than likelihood ratio test and more efficient, more robust than the Wald test. So that's why for many cases, when people cannot afford to fit 2 models, they go with the score test. Okay. I think that is the good, how to say, I think that is the application of each one. And any questions? So maybe I can ask you several questions for you to think about just as a way to summarize. So for sample size, if we have a large sample size, it's actually good for all 3 tests, right? But as the sample size goes large, you also have a heavier computational burden. Maybe depending on how your MLE is computed, maybe the MLE will be too slow if n is large. So in this case, maybe you can only go with the score test. Since small sample size, only go with the score test. For Wald test, large sample size is good, but you need to make sure that asymptotic normality holds well. Otherwise, it's not good. Okay, and you have a good estimator for the variance. But for small sample size, like computation may not be a burden, and you may care more about statistical efficiency. So then it may be worth to go to LRT, use the likelihood ratio test since 2 or 4 the time. Okay. So that is the one thing I hope to just introduce briefly with application relevance. And another thing is regarding very important concept called nuisance parameters. So this is a general term. It can refer to any parameters, any model parameters not of interest. So how can this be? So for example, in the linear regression, linear model case, the error variance sigma square is not of interest. We're not interested in that parameter. We're only interested in the coefficient, but we must estimate that error variance. That's a nuisance parameter. And in the multivariate linear model, maybe we are only interested in one coefficient, okay? One covariance coefficient. But we do have other covariates to be accounted for to make the model more reasonable. For example, to adjust for confounders. And these other covariates parameters or coefficients are not of our interest, but they must be estimated. And these are nuisance parameters. So the question here is, how do we estimate these nuisance parameters when we fit the null model, when we fit the full model? So the short answer is for the score test, when we just fit the null model, we just put the parameter of interest theta to its null value, theta 0, and estimate the nuisance parameters as MLE. So we maximize the constraint likelihood. It's called, or restricted likelihood. It's called restricted MLE, meaning that we restrict our parameter of interest to be theta 0 and maximize the likelihood for other nuisance parameters. And for the LRT, we need to fit two models, a null model and a full model. And then for each model, we estimate nuisance parameters separately. So for the full model, MLE, joint MLE is going to be obtained by the parameter of interest and nuisance parameters. They all need values to maximize the likelihood. But for the null model, we restrict our parameter of interest to be theta 0, and then we only maximize nuisance parameter. Okay, so that's the short answer about how but this is a very key thing, and their estimation will actually affect how well we can do statistical inference for our parameter of interest. Okay, and finally, I'll talk about a generalization of our MLE, and this is called M-estimator. And you may see this in some context. What does it mean? So this M stands for maximizing a criterion or minimizing a loss function. So either way, depending on whether you set a criterion to be maximized to find your estimator, or you set a loss function to be minimized to find your estimator. So we can write it in one or two ways. So we can call M-estimate theta hat M as the maximizer. I write argmax of this criterion, which sums over your observations. And for each term in your sum, it involves one observation and your parameter of interest theta. So this is the maximized way to write it. And as one example, you can see that maximizing the log likelihood is one way, right? So MXI theta can be the log likelihood applied to the ith observation for your parameter theta. So this is the log likelihood for the ith observation. This is one way to look at it. So that's why MLE is a special case of an M-estimator because we are generalizing it. Another way is to look at theta hat n or theta hat n as the minimizer of a loss function. And for that, we can write I from 1 to n. I'm following some notation, rho xi theta. So in this case, rho xi theta is a loss. For example, we can have the squared loss. Yeah. So rho xi theta can be defined as xi minus theta squared. And if in this case, the least square estimator used in linear model, linear regression is also a special case of M-estimator. So M-estimator just generalized everything we have seen, okay? And the reason why it is introduced is that it can make it more flexible. For example, this can also make this loss function not a square loss, but like an so-called absolute loss or L1 loss, where we can consider the absolute value. And this is known to be more robust to outliers. Why is that? Because if you think about some data points, so in this case, if I'm just writing the square loss, the minimizer of it is the mean, right? But the minimizer of the absolute loss is the median. And median is more robust to the mean. And this robustness is based on this loss function. Because you can see for the square loss compared to the absolute value loss, data points farther away from theta will have much bigger influence on the square loss. So they will more drive the minimizer. While in absolute loss, they are less influential. That's the intuition behind it. So there is a field, and the M-estimator is particularly used as a useful generalization for the field called robust statistics. And it's actually about this, minimizing square loss or absolute loss, L2 loss or L1 loss. That's the robust statistic. But if we draw the two loss function, we can take a look. It's very interesting. So for example, let me just go down here. I'm just going to draw a loss. If this is my theta, okay, I'm just drawing theta and I'm looking at my value xi to see the loss it contributes. So if I have the square loss, it will look like this parabola shape, right? This is the square loss. And if I have just L1 loss, I'm just ignoring the constant, just trying to draw it. It can have something like this. It's not accurate drawing, but it's more like this. So two straight lines, right? So they may intersect somewhere. So then someone called Huber proposed the Huber loss, which actually bridges the two. So they try to obtain the smoothness close to the true value because otherwise it's not differentiable for the L1 loss. Try to keep the differentiation property of the L2 loss, but make the influence of outliers to be less, like the L1 loss. So it's a combination of both. So the shape of the Huber loss is like this. You first start with the L2 loss, and then starting from somewhere, you follow the L1 loss here. So on the left-hand side, same thing. You start with the L2 loss, and then you be like parallel to the L1 loss for large values. So you try to have a good property of both. And Huber loss forms the foundation of robust statistics. But of course, nothing comes free, right? So the L2 loss is advantageous for its computational efficiency. You can easily get differentiation result, but you lose the robustness. But if you want to be more robust, then Huber loss is the middle ground between L1 loss and L2 loss. And since you can see using the Huber loss, this loss term can get a little more complicated form. And if we want to study how such a minimizer as an estimator behave, we need some theory, and that is the M-estimator theory. So essentially, under some, again, regularity conditions, people can study asymptotic normality of M-estimator, which can be considered as a generalization of MLE. Because in this case, you directly work with minimizing a proper loss, but not arguing the likelihood or log likelihood. Okay, so I think that is the thing I hope to just offer as some end notes. Essentially, this large sample theory class concentrated studying behaviors of estimators, right? We talk about many estimators, including estimators that started from the sample mean in the central limit theorem and its variants, like different types of sample moments, right? We using sample moments as natural estimators for their corresponding population moments. What is the behavior of those estimators? Talking about their consistency, their asymptotic normality, and the asymptotic normality for sample moments are extensions of central limit theorem, right? We actually talk about delta method, a very useful technique for transforming our central limit theorem to other variants. And we also talk about how central limit theorem can be still applicable with some violations, but not too severe. For example, the data are no longer IID, right? One is that they still follow the same distribution, but they are no longer independent, right? Then the M dependency is a weak type of weak dependence that can still make a central limit theorem work, or they are independent but not identically distributed. Then we need a Lindbergh-Feller theorem to make sure that in the average, not a small number of random variables dominate. That's essentially the thing. So you really have an average instead of dominated by one random variable. And then we talk about some other types of parameters and estimator, including using extreme order statistics to estimate boundary parameters, the parameter that define the boundary of your parameter space, and also quantiles, right? Sample quantile for population quantile. We also talk about those, and these are very useful things, especially if we think about sample quantiles, they are closely related to robust statistics. Sample median is more robust than sample mean. And then we spent quite some time, and this is something I added as new material this year, MLE, right? MLE theory, that's a very big part of it. And also the conditions, especially conditions for it to hold well, which is mostly regularity condition on the data distribution. And then efficiency, right? Efficiency means that we can compare different estimators if they both are asymptotically consistent and asymptotically normal. How can we see which one is more efficient? We compare their asymptotic variance. And then finally, just as today, we showed you one example about in the regression setting, the score test, Wald test, likelihood ratio test, different test statistics constructed by different rationale, but they do have their different advantages. Especially, it's always a balance of statistical efficiency and computational efficiency, right? What can you afford? That's the computation. And ideally, if your sample size is small, what can you ideally achieve? And that's statistical efficiency. And finally, M-estimator as the generalization of MLE. Oh, one thing I forgot to say is that we also talk about the V-estimator, U-estimator, and bootstrap, right? Density estimator. So these are in the context of statistical functional, where you are formulating your estimator in an abstract way as replacing. So first of all, you formulate your parameter in an abstract way as a functional of your true CDF. Then it makes sense to do plug in by replacing true CDF by the empirical CDF. You naturally get an estimator. And that is, and if your parameters function, if your parameter is an expectation functional, is an expectation of some functions, right, based on a sample drawn from your distribution. If it's that definition, then V statistic is the plug-in version of the expectation functional, but it will involve sample with replacement from your original sample. That's not good. It can lead to bias. And the U estimator corrects the bias, standing for unbiasedness. You basically require sample with replacement. Without replacement. That's the U estimator. And for Bootstrap, it is sample with replacement. And Bootstrap's first motivation is that if you have an estimator, you need to evaluate the estimator's performance, some performance metric of the estimator, like the bias or like the variance or like the distribution. But you only have one sample. How can you evaluate that performance metric? So it try to do that plug in into the performance metric by using the same sample again. But now you're doing sample with replacement to evaluate the performance. And we also talk about like the situations where Bootstrap actually hold. Again, I think it's usually when your estimator is more like a centralized estimator, like the mean or the median, right? It's based on your sample's central properties. It's not extreme order statistic. For extreme order statistic, it's usually many things break down. So yeah, and also density estimator is also plugging, except that we're not directly plugging in CDF, but we're trying to plugging in for PDF estimation. Yeah, so we try to cover many topics, but for many things, we just give you a very high level idea and not able to show you many examples. But hopefully this will be a good roadmap if you want to learn more along the way. Yeah. Okay, so I think I will try to stop here and then I'll see you next Wednesday. I'll see you on next Wednesday on Zoom to do the presentation. I'll send the link. So, and just watch out. I think I sent the announcement already, but just try to follow the deadlines in the announcement. And briefly, next Wednesday will be your final presentation. And 1 week after, it will be the due date for your paper. Okay. Okay, bye everyone.